Now let's talk about transposition. Let A be an n by n matrix with entries aij. The transpose of A, written as A superscript T, is the n by n matrix whose rows are the columns of A in the same order. That is, A transpose has the entries aji. This means that the ith row of A transpose equals the ith column of A. It is also true the other way round. That means the jth column of A transpose equals the jth row of A. Let's look at some examples. Suppose I have a matrix A, which is a column vector with entries 3, 1, and 4. Since A has one column only, A transpose has one row only, and the entries are also 3, 1, and 4. Now suppose B is a row vector with entries 7, -3, and 6. Since B has 3 columns, each with one entry, B transpose has 3 rows, also with one entry each, and again they are 7, -3, and 6. Now C, which is the matrix 3, -1, 1, -2, -4, and 8, it has 2 columns, each with 3 entries. So the transpose of C has 2 rows, and each row has 3 entries, where the first row is 3, 1, and -4, and the second row is -1, -2, and 8. Now D is a square matrix with entries 2, 0, -5, 3, -1, 9, 7, 6, and -4. Since D has 3 columns, each with 3 entries, the transpose of D has 3 rows, also with 3 entries each. So again, the transpose of D is a square matrix with size 3 by 3. Its rows are 2, 3, 7, 0, -1, 6, -5, 9, -4. There is another way to think about transposition. For a matrix A with entries aij, the entries A11, A22, up to ANN form the main diagonal of A. For example, for these 3 matrices, the main diagonal entries are the ones circled. In this case, transposing A is the same as reflecting A about its main diagonal. We can use these 3 matrices to illustrate. For the column vector 3, 1, -4, to take its transpose, we first copy the matrix and draw the main diagonal. Then we reflect 1 and -4 as shown. Therefore, the transpose is this row matrix. For the second matrix, to take the transpose, we first circle the main diagonal. Then we swap the entries 1 and -3, and reflect -4 and 5 about the main diagonal. So we obtain this matrix. For the 3 by 3 matrix, to form its transpose, again we circle the main diagonal. Then we can swap the entries 1 and -3, -4 and 7, 5 and 9. We get this matrix. Notice that the main diagonal entries are fixed in transposition, so they always remain in their original positions. Let's look at some properties of transposition. Let A and B be n by n matrices. Then, the first property is that A transpose is equal to A itself. The second property is the transpose of K times A equals K times A transpose for all real numbers K. The third property is that the transpose of A plus B equals the transpose of A plus the transpose of B. The first property follows from the definition in the sense that if I swap the rows and columns of A and swap again, is the same as not swapping. For the second property, we write A to have the entries aij. Then K times A has the entries K times aij. So the transpose of K times A is the transpose of the matrix with entries K times aij. Since every entry is multiplied by K, there's no change to k when I swap the rows and columns, so this is equal to the matrix with entries k times AJI. Now I can take k outside the matrix to have k times the matrix with entries AJI, which is equal to k times A transpose. For the third property, we write A as the matrix with entries Aij and B as the matrix with entries Bij. We also write A plus B to be the matrix with entries Cij, where Cij equals Aij plus Bij. Then the transpose of A plus B is equal to the matrix with entries Cij transposed, which equals the matrix with entries Cji. But Cji equals Aji plus Bji, so we can break this off into two matrices, one with entries Aji and the other with entries Bji. So it is equal to A transpose plus B transpose, and the proof is complete. Let's finish off with the definition, which states that a square matrix A is called symmetric if A transpose equals A itself. For example, the 2 by 2 matrix 1, negative 1, negative 1, and 2, and the 3 by 3 matrix 3, 2, 6, 2, 0, negative 7, 6, negative 7, negative 4 are symmetric matrices. We can see that these matrices show a reflectional symmetry among the main diagonal, in the sense that if I reflect the entries about the main diagonal, we get back the same matrix.